One of the biggest challenges in building AI that's genuinely smart is memory. And I'm not just talking about remembering your last question. I mean, a real long-term memory that lets an AI actually learn and grow over time. So, how are we doing it? Well, right now, there are two main ways, and we're about to break them both down. Just imagine for a second, you've got this incredibly powerful AI assistant, but it has complete amnesia. Every single time you talk to it, it's like meeting for the first time. It has zero memory of you, your projects, or any of your past conversations. How useful would that be for anything complex? Not very, right? And that's really the heart of the problem for developers. Without memory, an AI is basically just what we call a stateless function. It takes your input, spits out an output, and boom, forgets everything. This is the huge leap we have to make to go from a simple chatbot to a truly autonomous agent that can handle long-term, complicated tasks. Okay, so how do we solve this memory problem? Well, the first and by far the most common solution, the thing that's become the industry standard, is the vector database. You can think of this as the AI's semantic memory, which is a fancy way of saying it remembers things based on their meaning. So how in the world does that work? Well, a vector database doesn't just store text like a normal database. It stores something called embeddings. And you can think of embeddings as a kind of numerical fingerprint for the meaning of a piece of text. The closer two of these fingerprints are in this high-dimensional space, the more similar their underlying concepts are. It's kind of like organizing a massive library by the actual ideas in the books, not just by alphabetical order. It's pretty cool. Getting the data into the system is actually a pretty straightforward three-step process. First, you take your raw data, say a bunch of chat logs, and you split it into smaller, manageable chunks. Next, you feed those chunks into an AI model, and its job is to turn each one into a numerical vector. That's your embedding. And finally, the database takes all those vectors and indexes them, which is basically just organizing them so it can perform searches at lightning speed. And the upsides here are really obvious. These things are incredibly fast. We're talking searching through billions of items in milliseconds. They're also relatively easy to set up, and they're fantastic at what's called fuzzy matching. That means they can find what you're looking for even if you don't use the exact right words or you spell something wrong. It's why they are the absolute go-to for handling messy, unstructured data like conversations and documents. But, and there's always a but, there's a catch. For all of its power, this kind of semantic search has one major blind spot: multi-step logic. It really struggles to connect the dots when the answer isn't in one place, when it requires putting a few pieces together. Let me show you what I mean. All right, so imagine the AI's memory has stored this one simple fact. Project A uses technology B. Easy enough, right? The system gets the relationship between Project A and technology B. Now, somewhere else, maybe in a totally different document, it has another little nugget of information. Technology B has a dependency on component C. And again, it can embed this and find it if you ask about technology B specifically. So here's the million-dollar question. Can the AI make the logical leap and connect Project A all the way over to component C? And the answer, a lot of the time, is no. Because these two facts are just two separate embeddings floating in the database, a simple similarity search is probably going to miss that indirect link. This is the real weakness of a purely semantic memory. And this is exactly where our second architecture makes its grand entrance: Graph RAG. Now, RAG stands for Retrieval Augmented Generation. That's the whole process of grabbing relevant info before you generate an answer. GraphRag just takes it to the next level by retrieving that info from a structured memory that's all about explicit relationships. The best way to think about GraphRag is like one of those detective corkboards you see in movies. The nodes are like the photos of your key pieces of evidence, the people, the projects, the tech. And the edges, well, those are the pieces of red string connecting them, defining really clear relationships like uses or depends on or is part of. So instead of just searching for things that seem similar, the AI can literally follow the strings to uncover deep connections. And this approach is just incredibly powerful. It gives you super precise answers because it's built for exactly that kind of multi-step or multi-hop reasoning that vector databases have trouble with. But maybe the most important thing is that it gives you explanation ability. You don't just get an answer, you get to see the exact path of connections the AI followed. That kind of audit trail is absolutely critical in a business or enterprise setting. But of course, all that power comes with a price. Building and maintaining a knowledge graph is seriously complex. For starters, you need a whole other pipeline just to pull all those entities and relationships out of your text. It also has a cold start problem, meaning it's not very useful until you've poured a ton of data into it. And unlike the super flexible world of vector databases, the structure or the schema of a graph can be pretty rigid and tough to change. So now we have these two very powerful, but also very different ways of thinking about AI memory. Which one should you actually use? Well, let's put them head to head. The choice really boils down to what you're trying to do. As you can see here, vector databases are your champion for messy, unstructured data where you just need a good, broad search. But when you're dealing with highly structured stuff, like a company's code base or their financial records, a graph's ability to run these precise relational queries is just unbeatable. It's that classic trade-off, right? The low cost and ease of vectors versus the high cost, high precision power of graphs. So it's one or the other, right? You have to pick a side. Well, what if you didn't have to choose? The most exciting systems being built right now aren't picking one or the other. They're actually creating a hybrid memory that combines the strengths of both. Here's how this hybrid approach works, and it's really elegant. First, the agent uses the vector database to do a quick, broad search, just to get into the right neighborhood. Then, the top results from that search become the starting points, or entry nodes, into the knowledge graph. From there, the system can follow those precise, structured connections to find the exact, detailed context it needs. And this approach perfectly marries the broad, fuzzy recall of a vector search with the strict, deterministic precision of a graph. It's genuinely the best of both worlds. You get the speed of one and the pinpoint accuracy of the other, all working in harmony. So what's the practical takeaway for you? What should you do? The best practice that's really starting to emerge is to think in layers. You start with a vector database. It's fast, it's simple, and it gives your AI a solid foundation of memory. But then, as your agent's reasoning needs get more and more complex, you strategically start to layer in a knowledge graph to handle those really critical, multi-step connections. All of this leads to a pretty fascinating question when we look to the future. As these memory systems get more sophisticated, and as AI agents become truly autonomous, they won't just be remembering what we tell them to. They'll start making their own decisions about what's important enough to keep. So the real question becomes, what will they choose to remember? And maybe even more importantly, what will they choose to forget?